I don't. Time to do Gauss's law. Okay, what we're going to look at here is a kind of quick video covering Gauss's law. It is something that's primarily used in electricity and magnetism in the world of physics. And it really allows us to either look specifically at an electric field, or it allows us to look at the charge enclosed inside some region. In general, Gauss's law kind of takes a somewhat interesting form if you're not exactly familiar with a lot of calculus. It takes the form of a closed integral of an electric field dotted with some area, a surface area, if you will. And this is equal to a enclosed charge, and we'll talk about exactly what we mean by a closed charge in a little bit, divided by epsilon naught, the permeability of free space. So what we see here, and what we're really going to focus on right now, is we're going to focus on this integral, because that's probably the thing that is the most confusing for someone when they're first starting to use Gauss's law, but it's also the quickest thing to be able to determine and work out. Even though this symbol here, this closed integral, looks like really weird and different, the idea of Gauss's law is really simple, and we actually don't really need to concern ourselves with the idea of the integral, but really just focus on what Gauss's law is saying. Now, it's kind of easiest to see in an example. So let's just take a spherical distribution of positive charges. Okay, they're just there. You just, maybe take an insulator, rub it with some cat fur or something like that, and then boom, you've got charges there. Let's just say it's positive for the sake of argument. If you had this positively charged item, it's going to have an electric field pointing away from it. And if we, let's just claim for sake of argument that these charges are uniformly distributed, then this electric field is uniform as well. And even though we draw it in 2 dimensions on the page, we really need to start thinking about this E field as a spherical distribution. So everything's going in all the directions. Okay? What we're going to do is we are going to create a Gaussian shell around our object. And the key with these Gaussian shells is that we really use the idea of symmetry to make the shells easier, and whenever we're doing these shells, we really need to pay attention to this symbol right there. That's not a multiplication symbol. This is technically known as a dot product. And what we mean by that dot product is, hopefully you remember, that this isn't just E times A, but it's E dA cosine of theta, where that cosine is that dot product. We're looking for vectors that are in the same plane as each other. And for a cross-sectional area, or any surface, the way we define the plane is a vector perpendicular to that plane. So if I wanted to think about creating a shell around this sphere, then the best shell to make is a sphere. If I make a sphere that perfectly encloses this, then I have enclosed all of the charge here, and I know what the surface area of a sphere is. Since I used a sphere, whenever I take this integral, this closed surface integral of dA, and what's actually going to happen is, since this electric field is constant, I can pull it to the outside if you're familiar with the integrals. Since I'm just integrating dA, or finding the surface area of a sphere, I don't really need to do any crazy math here. We know the surface area of a sphere. It's just a known fact. It's just 4 pi r squared. That's it. If you wanted to be like, whoa, that was amazing, where'd you get that from? Technically, if you know the volume of a sphere, 4/3 pi r cubed, and you take the derivative of that, you'll get yourself a surface area. But that's just what dA is. If you go over the entire sphere, that's its surface area. So because of this, if we just have this charge distribution like so, this entire equation up top, this E dot dA, or the closed integral of it, equals Q naught, or Q over epsilon naught, it's really just going to become for us that E times 4 pi r squared equals the charge enclosed over epsilon naught. And that's it. If you know the charge enclosed, then just divide by 4 pi r, so that your electric field now equals the charge enclosed inside that shell divided by that free space constant, 4 pi r squared. And that's that. That's all Gauss's law is there. What we can do with Gauss's law, though, is we can apply it to some more complicated scenarios. Instead of just having, a perfect sphere of charge in space, what we can also have is a line of charge. Let's pretend I have like a wire that has a charge distribution on it, or let's just say it's uniformly charged to make life easy. What we could then do is we could enclose this wire in a Gaussian surface. And normally whenever we draw these wires, it's kind of easiest to go like this, because normally they do give you some sort of charge distribution on them. But we just enclose this in some sort of Gaussian sphere. We just say, hey, look, whoosh, seal it up, thump, thump, ching. And now you have that object inside the Gaussian surface there. If you wanted to find it at some arbitrary distance r on the outside, you could. What you want to be careful about, though, is most of the times the way these kind of work is that our wire will want to find what the electric field is out to the radius of the wire, because as this charge goes in here, you're accumulating more charge because you're obtaining more area and volume. So normally we'll set up that Gaussian surface right here, and we'll do a Gauss's law for that. And then if we want to see what it is outside of the wire, like we go beyond that radius, we set up a second Gaussian loop or surface further out, so we can get what happens whenever your radius goes beyond. But in the end, this kind of Gaussian setup is still the same. We made a cylinder here, and the reason why we made a cylinder is that if we think about the electric field coming out from this cylinder of wire, it's coming out normal to the surface everywhere. And the only way we can capture that line coming out from a cylinder is to throw another cylinder around it, because then it'll be normal to that surface. And getting the area of the side of a cylinder, of kind of that soup label, is a fairly straightforward thing to do. If we think about a circle that has some length to it, we're just unrolling it. So what's actually going to happen is this has some length here, L, but there's also a radius. And our surface area of a cylinder is actually just going to be 2 pi r. That's how much you've unrolled in terms of a length. So you have some length like this from your unrolling times L, because that's just how long this is. And if you connect that, look, you have a big old area, just like a square. So if you wanted to Gauss's law this, we could just say, hey, look, here's your closed integral, E dot dA equals the charge enclosed over epsilon naught. And then in this case here, whenever we take the closed integral on dA, we're just getting this area. So we can just say that our electric field times 2 pi r L equals Q naught enclosed over epsilon naught. You do want to be careful here. You're going to have different values when you're inside and outside the cylinder. When you're inside the cylinder, this might be some hard radius r that you can just say, hey, look, like I'm at this value of r. But whenever you go outside that cylinder, you're at some other arbitrary value. So most of the time, what's kind of the proper thing to do here is just leave this as little r, because you don't know where you're at inside the cylinder anyways. You could be at the edge, you could just be on your way out, whatever. What really you need to be aware of is, depending on where you're at, your charge enclosed may change. If you're still inside the cylinder, you haven't picked up all the charge yet. You've picked up some amount of charge, and you really have to look at your charge distribution there. If you're outside the cylinder, great, you have everything. Everything is inside your Gaussian surface, your cylinder, you're fine there, okay? But it is something to be careful about. So whenever you're doing some examples, definitely take a look at the wire, see what they give you, see what you're doing for that. There are some other shapes we can do with our Gaussian surfaces. If we have a plane of charge, so I just have a plane out in space, and let's just say it has a uniform charge distribution on it, such that if it is positively charged, it has an electric field moving away from it. But it actually has that electric field acting in two directions, so be careful about that. What we'll actually do here is we use a cylinder again, but this time instead of using the side of the cylinder, we're going to use the top and bottom. We're going to use like the lid, whoa, and the bottom of the can. Oops. By doing this, the cross-sectional area that we want, or the surface area we want, is actually just this circle here and this circle in the bottom. So if we once again just set up our closed surface area integral equaling the charge enclosed divided by epsilon naught, we actually have here the area is just equal to pi r squared of, whatever you want that circle to be. What we need to be careful about is, in this case, we have not just one but two areas. So the total area we have is actually 2 pi r squared. One for the top, one for the bottom to catch all the flux. So what we can say here is just that the electric field times 2 pi r squared equals the charge enclosed over E naught. So that's just another way you can do another Gauss's law, this time for a plane of charge. Those are kind of like big three that you can do Gauss's law for: a cylinder, a sphere, and a plane of charge. Technically, you can also use a similar idea of Gauss's law for a line of charge, but depending on how you like to think about that, it might be easier just for you to integrate the charge density down, looking at something of that nature. But these are kind of our big ones that we're looking at here for Gauss's law. And really, for Gauss's law, remember, even though it does have this weird kind of form, this dA here, it really just represents what is your surface area. For a sphere, it's 4 pi squared. For our cylinder, where we're using the sides, it's just 2 pi RL. And for a plane, where we're once again using a cylinder, it's just our pi r squared values, but we've got 2 of them this time. So that's the idea of Gauss's law, and we're just taking some electric field and the flux of it, passing it through some surface, and by that it's enclosing some charge with a permeability of free space there. Okay? Hopefully that gives you a better idea of how to kind of approach a Gauss's law. It's definitely something that you'll want to do 5 or 6 times before you really start getting a feel for the problems and what they begin to ask for. But hopefully that helped you out. With that, kind of an overview of Gauss's law is finished. Take it easy. Okay, everybody, I'm leaving. Nobody's here.